Hey there, and welcome. Today, we're diving into some of the invisible forces that literally shape our world. We're talking about that deep, powerful connection between electricity and magnetism.
So just imagine for a second. What if every time you flip a light switch, you're not just making a bulb glow? What if you're actually sending out invisible ripples, creating a disturbance in the very space around that wire? Sounds a little like sci-fi, I know, but that's the fundamental truth we're going to uncover today.
And our story starts not with some grand, complicated plan, but with a simple, totally unexpected observation. It's a classic tale of pure curiosity that led to a discovery that, no exaggeration, powers our entire modern world.
Picture this. The year is 1820. A scientist, Hans Christian Ørsted, is in the middle of a lecture. He flicks on an electrical circuit, and a compass sitting nearby suddenly twitches. The needle just moved. That simple, complete accident was about to change everything.
So what's the big deal? Well, a compass needle only moves when there's a magnetic force around. So that little twitch was the first real, solid proof that an electric current creates its own magnetic effect. Suddenly, these two forces weren't separate things anymore, they were connected.
Okay, so before we dive into the magnetic field that electricity makes, let's take a step back and get a handle on what a magnetic field even looks like. And to do that, we're going to start with something we've all played with, a simple bar magnet.
This is a classic experiment. You might have even done it in school. You just take a bar magnet, put a piece of paper over it, and then sprinkle some fine iron filings on top. Give the paper a few gentle taps, and something pretty amazing happens.
That random dust of iron filings just snaps into this beautiful, perfectly ordered pattern. What you're seeing is a map. It's a map of the invisible force field that's all around that magnet. We can't see the force itself, but we can sure see its effect.
So what do we call this area of influence? Well, it's the magnetic field. It's just the space around the magnet where you can actually feel or detect its force, whether it's with iron filings or, say, a compass needle.
And those clear lines that the filings make, we call them magnetic field lines. Now, they're not real lines, of course. You can't touch them. But they are a fantastic way for us to visualize the direction and the strength of that invisible field.
Now, these lines aren't just random. They follow some very specific rules. They always flow out of the North Pole and loop around into the South Pole, forming these complete, unbroken curves, and they never, ever cross each other. Most importantly, look where the lines are all bunched up close together. That's where the magnetic field is the strongest. Okay, so now we get what a magnet's field looks like. Let's bring this all the way back to Ørsted's discovery and finally uncover electricity's big magnetic secret.
This, right here, is the game changer. Just like a bar magnet, a simple wire with electricity flowing through it creates its very own magnetic field. The simple act of electrons moving is enough to create a magnetic force in the space around that wire. And we can prove this has a clear direction. Check this out. If you run a current from north to south over a compass, the needle gets pushed and points east. But what? What happens if you reverse the flow? Send the current from south to north instead. The needle's deflection flips too. Now it points west. See? The takeaway is crystal clear. This isn't random at all. It's a direct cause and effect thing. The direction of that invisible magnetic field depends completely on the direction the electric current is flowing. You change one, you automatically change the other.
Okay, but this is where it gets even cooler. If a straight wire makes a field, does the shape of that wire matter? I mean, can we actually bend and sculpt this invisible force just by bending the wire? Well, let's find out.
So if we take a straight wire, poke it through a piece of cardboard, and do our iron filings trick again, a totally new pattern appears. Perfect concentric circles, centered right on the wire. And just like with a regular magnet, the field gets weaker the farther away you get.
But what if we take that straight wire and bend it into a loop? The field actually changes with it. The lines all start to concentrate inside that loop, becoming way stronger and straighter right there in the middle.
Well, that leads to a pretty logical next question, right? If one loop concentrates the field, what happens if we make lots of loops? What if we wrap that wire into a tight coil?
This specific shape actually has a name. It's called a solenoid. It's basically just a long coil of wire. And when you pass a current through it, something really remarkable happens to that magnetic field.
And here it is. The fields from every single one of those little loops add up, they amplify each other, and they create a pattern that is almost identical to a permanent bar magnet.
We've basically just built a magnet, an electromagnet that we can turn on and off with a switch.
So we know there's a field, we know its direction depends on the current, but how can we figure out its direction without carrying around a compass and a bag of iron filings? Well, turns out there's a super convenient trick, and you have all the equipment you need attached to the end of your arm.
It's called the right-hand thumb rule, and it's dead simple. All you do is imagine grabbing the wire with your right hand, point your thumb in the same direction the current is flowing, and voila, the direction your fingers curl is the exact direction of the magnetic field lines.
So when you boil it all down, electricity and magnetism aren't just related, they're two sides of the exact same coin. The flow of one creates the field of the other in this really beautiful and predictable dance that powers, well, pretty much everything.
So, we figured out that electric current creates its own magnetic field. But what happens when you take that wire with its own little field and you put it inside another magnetic field? What happens when these two invisible forces start to interact and push on each other? Well, that's when things get really interesting. And it's a question for our next explainer.